Welcome back to ECE 320A. This is another video in Unit 6, and homework number 6 will be due at the completion of this unit, and exam number 3 will be coming up at the end or after completing unit number 8. We want to be completing chapter 12, which is dealing with, in the end of chapter 12, is dealing with inverse Laplace transforms. And I've been hinting at there being different ways of finding these residues or these partial fraction expansion coefficients. We've looked at the cover-up method. That works really nicely with distinct roots. It works for some of the terms when we have repeated roots, but when we have repeated roots, we have to typically start relying on other strategies or techniques. And in this video, we'll talk about 4 of those techniques. One we've already seen, which is picking a convenient value of S. Another one looking at letting S go to infinity on both sides of the expression after we do some manipulating, and essentially that manipulating is multiplying everything through by S on both sides of the equality. Another strategy is to find a common denominator, and now if we had 4 unknowns, that would generically lead to 4 equations in 4 unknowns, and we could solve that using any linear algebra technique. The last approach that we will talk about involves differentiation. And we're mentioning it last because a lot of students may not want to start differentiating these polynomials that have high powers involved, or s plus 5 cubed, for example. Maybe they don't want to be differentiating that when that expression is in the denominator. Let's now look at working through some examples to help illustrate these different strategies for finding partial fraction expansion coefficients, or these residues. Again, we've been using the cover-up for distinct roots, but that doesn't always have to be the case. You can use these partial fraction expansion techniques not only for repeated roots, but also for distinct roots, and in some cases it may be to your advantage or benefit to do that in terms of easing your computational burden. Let's look at the first one, and we've already done this in a previous video, so let's do it for a different transform. And again, if we're inverse Laplace transforming, the very first question we need to ask is our transform strictly proper? In this case, our denominator is second order, our numerator is first order, and so we can immediately write down the partial fraction expansion expression for this particular transform. And in this case, it's actually then going to be a1 over s plus 7 squared plus a sub 2 over s plus 7. And we only have that one factor. It's repeated twice. We now end up with 2 terms in our partial fraction expansion representation. And now, which of these coefficients, a sub 1 or a sub 2, can we actually apply the cover-up method for? In this case, we can use the cover-up when we want to find the coefficient associated with the highest power of that repeated root, which in this case we have a root that's repeated twice. We have a1 sitting on top of that particular factor, which is s plus 7 squared. So we can use the cover-up method to find a sub 1. And the cover-up now says multiply both sides through by what's underneath a1, which is s plus 7 squared. So on the left we have 3s plus 5, and we evaluate that at s equal to minus 7, which now gives us 3 times minus 7 plus 5, or we have minus 21 plus 5, or a sub 1, is now minus 16. That was a sub 1, which was s plus 7 squared times f sub a of s, all evaluated at s equal to minus 7. Now we need to find a sub 2, and we can't invoke that same strategy. We can't multiply by s plus 7 and evaluate at s equal to minus 7 and hope to find any way of isolating a sub 2. That's just not going to happen. So now what we want to do is let's pick a convenient value for s, and in this case we can't pick a value of s that causes that denominator to vanish in any of our factors, and in this case the only value of s that causes that to happen is s equal to minus 7. So as long as we avoid s equal to minus 7, any other value of s is valid. So in this case, let's go ahead and use a common one. Let's say s is equal to 0, and let me just say that you can't use s equal to 0 if s equal to 0 is a root of the denominator. So if we did have a pole, let's say that we did have a root there, then we would have plus a sub 3 over s, and we couldn't use s equal to 0. But we might be able to use, or we could use s equal to 1, for example, and then that doesn't mess up or make our algebra too complicated, and it's not going to cause any problems in evaluating for the unknown, which in this case is a sub 2. So now let's find a sub 2 by substituting s equal to 0 into that partial fraction expansion expression. We have 3. If we look at the numerator, we had 3s plus 5, so we now have 3 times 0 plus 5 all over s plus 7 squared, and that's equal to now minus 16. That was our a sub 1 that we just found, over s plus 7 squared plus a sub 2 over s plus 7 raised to the first power. And now we might want to just multiply all things by s squared. That might simplify things a little bit, and that leaves us then with 5 on the left. The 3 times 0 is gone, and we've now multiplied by s7 squared, so we now have 5 on the left, minus 16 for the first term, plus 7a sub 2. Since we had 7 squared divided by 7, we now have 7a sub 2. Or if we now divide both sides by 7 and take that, or add 16 to both sides, we have 21 equal to 7a sub 2, or a sub 2 now becomes 3, which now means that f sub a of s, our partial fraction expansion, is now minus 16 over s plus 7 squared plus 3 over s plus 7. And that now allows us to take that into the time domain. F of t is now minus 16. Now that that's repeated, we need to put a t in front of it. We have minus 16t e to the minus 7t plus 3 e to the minus 7t, t greater than or equal to 0. And that's now our time domain expression for the first example where we were using a convenient value of s. Let's now look at the second approach, which is a limiting expression. And here I'm just sort of illustrating that by limit of some quantity as s goes to infinity. Let's see what that technique looks like. Here are the steps involved in using this limiting expression technique. First, we multiply both sides by s. So now we're going to put an s in the numerator of all of our terms. Then we take the limit as s goes to infinity, and that hopefully will then allow us to isolate on the unknown, which in our case is a sub 2, going back to an earlier example. So suppose we have now 2s plus 1 over s plus 1 squared times s plus 2, and we now say that's equal to the partial fraction expansion. We have one term associated with the s plus 1 squared factor. We have another term associated with the s plus 1. And we have a third term, which is all the terms that we're going to have associated with the s plus 2. Again, this is strictly proper, so we can go ahead and immediately find the partial fraction expansion. A sub 1, let's just assume that we already have computed that, and we have in the past. That's actually minus 1. A sub 3, we've already computed. That's minus 3. And now what we want to do is multiply or use this limiting technique. So the first thing that we do is multiply everything by s. Now we have everything multiplied by s, and we want to now take the limit as s goes to infinity. On the left, we now have, the key here to make your job a little easier is to focus on the highest power of s in the numerator and the highest power of s in the denominator after you've multiplied everything out. Meaning, on the left, we have 2s squared plus s in the numerator, and the leading or the highest power term is 2s squared. So we focus on 2s squared. Downstairs on the left, we have s squared times s, or we have s cubed. So that now we're looking at taking the limit as s goes to infinity of 2s squared over s cubed. So effectively now we have 2 over s, and we're looking at the limit as s goes to infinity. And this was available to us because we had 2s squared over s cubed, which now is 2 over s. That's where that's coming from. The limit of that expression then, as s goes off to infinity, I hope you can see that the denominator dominates. The 2 is okay. It's just sitting there. So on the left, we actually end up with 0. Now we take the limit as s goes to infinity of these three terms on the right. The first term is minus s over s squared. That now becomes minus 1 over s, and as s goes to infinity, that's just 0. The middle term is now a sub 2s over s. As s goes to infinity, s is marching off to infinity at the same rate in the numerator as the denominator. Those s's then cancel each other out, and we're left then with a sub 2. And then on the right, we have minus 3s over s in terms of the leading powers or the highest powers of s. Those s's are marching off at the same rate, so we're left with then minus 3 in that last term. This now allows us to conclude that a sub 2 is equal to 3, and that we could then use to find the exact partial fraction or inverse of that partial fraction expansion, which we won't do. We've already done that for this example, but that a sub 2 should be consistent with what we've already found using a convenient value of s in a previous video. That's the second strategy, which is the limiting, and you can see that with that limiting, a lot of terms vanish and we're left with isolating a sub 2 with whatever is left over. Let's now look at a common denominator technique for finding these residues, and it too is a three-step process. First, we obtain a common denominator on all the terms. Then we focus on, since the denominators are equal, since we found a common denominator, we can essentially forget about the denominator and worry about the numerator. And once we're in the numerator, we can just start equating coefficients of like powers of s. That will then produce, however big or whatever order that numerator is, that will provide us with that number of equations in the unknowns, where the unknowns are our partial fraction expansion coefficients. So let's apply that to our previous example. We now have the left-hand side, that's already over a common denominator, but to get that denominator common on each of the three terms on the right, we now need to take a sub 1 and multiply that by s plus 2. And now if you simply look at this piece, you can see that that returns that particular expression. So we haven't changed the expression on the right yet with that common denominator. And we don't want to make any such changes. We can't add something non-zero. We can always add zeros, but we can't add anything non-zero to one side and not the other. A sub 2, what do we need to scale it with? Well, it's missing an s plus 1 factor, and it's also missing an s plus 2 factor. And finally, a sub 3, to get it over the common denominator, we need to scale it by the s plus 1 squared term. Now to maybe make this a little cleaner, let's go ahead and multiply these out. We now have s squared plus 3s plus 2. You could use FOIL or whatever convenient strategy you have for multiplying linear factors in polynomials. Here we have s squared plus 2s plus 1, and now we can use that to start identifying all of the different pieces. Let's now look at the powers of s that are available or present in the numerator. We have an s squared, and what is scaling, or what coefficients are sitting in front of s squared? We have an a sub 2, and we have an a sub 3. Then we have our s terms. We have an a1 plus a 3a sub 2 plus a 2a sub 3 times s. And then we have our constant terms. We have a 2a1 plus a 2a sub 2 plus an a sub 3. And those are now all sitting in the numerator, and the left-hand side numerator, 2s plus 1, needs to equal this right-hand side numerator, which is now in terms of these unknown coefficients, a1, a2, and a3. And we can find these unknown coefficients by realizing that on the left there is no s squared coefficients, so that's 0 is equal to a sub 2 plus a sub 3. So let's now write that down for each of the different coefficients associated with the different powers of s. We have an s squared set of coefficients. On the left, 2s plus 1 has nothing for an s squared coefficient, and on the right we have a sub 2 plus a sub 3. There's one of our three equations for these three unknowns, a1, a2, and a3. Looking at the s1 coefficient, we have 2 on the left, and on the right we have a sub 1 plus 3a sub 2 plus 2a sub 3. And finally, for our constant, we have 1 on the left, and on the right, we have 2a1 plus 2a sub 2 plus a sub 3. And now we have 3 equations in these 3 unknowns. And if we hadn't yet found any of those A1s, A2s, or A3s, we could now solve that using any linear algebra approach that we want for solving 3 equations and 3 unknowns. If we put these equations in a matrix, we're trying to solve for A1, A2, and A3. Suppose we look at the very first equation. There is no A1. There's one A2 and one A3, and that A2 plus A3 needs to equal 0. We now have the top row in this set of matrix equations. The second equation says we have 1A1, we have 3A sub 2's, and we have 2A sub 3's, and that combination of A's produces a value of 2. Finally, our last equation, which is coming from the constants in the numerator, we have 2a1s, 2a2s, and 1a3, and all of those equaling, or that combination equaling 1. Which, if we now say, let's just call this some M matrix, and this is now some B matrix, we can invert M and multiply that on the left of both sides of this equation and have M inverse times B, and we end up with A1 being minus 1, A sub 2 being 3, and A sub 3 being minus 3. And there's another strategy for finding these partial fraction expansion coefficients. Finally, our fourth technique for finding these residues is described in the textbook on the following pages, 447 to 451. And here's the stepped procedure to apply this derivative technique. First, we multiply through by the highest power of the root factor. We're used to doing that. Then we differentiate with respect to s. Then we evaluate at the root location and solve for the coefficient that we're after. Going back to our example, now we have f of s is n sub 2 of s over s plus 1 squared times s plus p sub 3. That produces this 3-term partial fraction expansion. The first step says multiply through by the highest power of the root factor, which in this case is s plus p1 quantity squared. We do that on the left and we do that on the right. On the right, that immediately isolates a sub 1. It leaves a sub 2 times s plus p1, and it has a sub 3 scaled by what we just multiplied through by, which is s plus p1 squared. But you can see then that if we now differentiate both sides of this, let's not differentiate the left because we're leaving f of s as some variable expression, but on the right, if we differentiate a1 with respect to s, that gives us 0. If we differentiate a sub 2s plus a sub 2p1 with respect to s, that produces a sub 2. And then we want to differentiate this last term with respect to s. That's a little bit ugly because it's now a quotient of 2 polynomials in s, but we now have the first piece, which is differentiating the numerator with respect to s, and that's now 2a sub 3s plus p1 over s plus p sub 3, and then we have another piece that is the result of the denominator being differentiated with respect to s. So there it's in the denominator. We have minus a sub 3s plus p1 squared over s plus p sub 3 quantity squared. If we evaluate those two terms at s equal to minus p1, those vanish, and so now on the right-hand side we simply have our unknown coefficient that we want, which is a sub 2, and that's equal to this left-hand side, which we would have to then find or compute and then evaluate at s equal to minus p1. So we evaluate the terms at s equal to minus p1. That canceled everything on the right-hand side other than a sub 2, and in our case that now leaves us with this expression, the first derivative of the numerator, the original numerator of f of s, which we called n sub 2 of s, divided by what's left in the denominator when we've now multiplied through by s plus p1 squared. That simplifies the expression a little, but we still have a messy differentiation maybe. But once we've differentiated, then after we've done that, we evaluate or replace s with minus p1, and that will produce this coefficient that we're after, which is a sub 2. In general, for an nth order root, this is the expression that will result. If we now have some numerator n of s, and again we're assuming that f of s is strictly proper, then we multiply through by s plus p0 to the nth power. We differentiate with respect to s, and each of these coefficients, and the coefficients or these residues are ordered consistently with how we have put the factors underneath. The highest power polynomial downstairs is sitting underneath a1. The next most highest is sitting under a sub 2, etc., down to the last power of s plus p sub 0, which is s plus p sub 0 to the 1. That's now sitting underneath a sub n, which if we then evaluate that at the different values of L, we would end up with this particular expression. Suppose we now look at applying this to a particular example. Suppose now that we have v of s is s squared plus 3s. That's in the numerator. In the denominator, we have s plus 1 times the quantity s plus 2 quantity cubed. First question, is v strictly proper? And it is. We have a fourth order downstairs and we have a second order upstairs, so we can now find the partial fraction expansion directly. Now if we use the strategy that we've been using, let's now start with a1. That's now on top of the highest power of s plus 2, which is s plus 2 cubed. Then we have a sub 2 over s plus 2 squared plus a sub 1 over s plus 2. And now we're done with the a's, but I need to make sure that I've subscripted those consistently. It's a1, a2, and a3 plus a sub 4 sitting on top of s plus 1. And what do we do now? Well, we probably don't want to be doing differentiation to find some of these that are immediately available to us. And immediately I'm saying maybe with the cover-up method. We can use the cover-up method to find a sub 4. That's a distinct pole. A sub 4 now is s plus 1 times v of s evaluated at the value of s that causes that factor underneath a sub 4 to vanish, which is the value of s is equal to minus 1, or we now have s squared plus 3s over s plus 2 cubed evaluated at s equal to minus 1. If we plug in minus 1 to that equation, we end up with actually minus 2. What other partial fraction expansion coefficient can we compute using the cover-up method? We can solve for the coefficient associated with the highest power of that repeated root, which in this case is a sub 1. So a sub 1 now is found by s plus 2 cubed v of s evaluated at s equal to the value that causes that s plus 2 polynomial to vanish, which is s equal to minus 2. We now have s squared plus 3s sitting on top of s plus 1, and we want to evaluate that at s equal to minus 2, and doing that we end up with 2. Now we have to use a different strategy. We could get a common denominator. We could pick two convenient values of s. We have two more coefficients to find, a sub 2 and a sub 3. But since we're trying to illustrate the last approach, which is this differentiation approach, let's now find a sub 2 and a sub 3 using the differentiation approach. A sub 2 now, if we go back to this formula, it's now 1 over 2 minus 1 factorial. So let me plug in the appropriate expressions. Then we differentiate with respect to s 2 minus 1 times, and what we're differentiating is the numerator times s plus 2 quantity cubed, which is really now just s squared plus 3s over s plus 1. And once we've done that, we then evaluate that at s equal to minus 2. So we can now perform the 1 over 1 factorial goes away, and we're just taking the first derivative, that's 2 minus 1, of s squared plus 3s over s plus 1. So now let's go ahead and do that as, let's just say, a product. So we have the numerator times the denominator polynomial, which is s plus 1 raised to the minus 1. So the derivative of the first term is 2s plus 3. That's still scaled by the denominator factor of s plus 1. Then we differentiate the s plus 1 to the minus 1 factor, which is minus the numerator times the denominator squared, essentially differentiating s with respect to s as 1, so that goes away, and now we have this all evaluated at s equal to minus 2. Which, if we simplified this, I think we would end up with something that is now potentially, if we put all of these pieces together, we would end up with s squared plus 2s. If we found a common denominator, which is s plus 1 squared, and now we evaluate that at minus 2, we should end up with a sub 2 equaling 3. Now to find a sub 3, we've already differentiated once, but let's go ahead and plug this into the formula. We now have 1 over 3 minus 1 factorial. The 3 minus 1 derivative with respect to s of s squared plus 3s over s plus 1. And again, once we've done all of that, we would evaluate it at s equal to minus 2. But this is now why it was convenient maybe to go ahead and compute that expression, which is the first derivative of what we have here, and now we need to differentiate what's in yellow one time. So a sub 3 now becomes 1 over 2 factorial, which is 1/2, the first derivative of what's now highlighted in yellow, which is s squared plus 2s plus 3 over s plus 1 squared. And once that differentiation operation is complete, we could evaluate that at s equal to minus 2. Let's go ahead and factor out the 1/2 so that we don't have to worry about that. We can differentiate the numerator, which is 2s plus 2, and then we differentiate the denominator, which is minus 2. The numerator is s squared plus 2s plus 3. We now have s plus 1, quantity cubed, and we're then differentiating s with respect to s. We evaluate all of that at s equal to minus 2, and that now leaves us with a sub 3 equaling 2. Which, if we do that and put it into the partial fraction expansion, you can check this, but now v of t will be equal to a1 times 1 over 2 factorial t squared, because a1 was sitting on top of s plus 2 quantity cubed, so we have t squared e to the minus 2t plus a sub 2 t e to the minus 2t plus a sub 3 e to the minus 2t plus a sub 4 e to the minus t, and that's now true for non-negative values of t. Now that we've shown all of these 4 different strategies, if you're fortunate enough to have a TI calculator that actually does symbolic manipulation, you can perform a short version. So if you now have the 89 or the 89 titanium or the TI Inspire, those will now allow you to actually just invoke the expand function. Now you would just say expand s squared plus 3s as the numerator divided by s plus 1 times s plus 2 cubed, close up all of the brackets, and that will produce 2 over s plus 2 plus 3 over s plus 2 squared plus 2 over s plus 2 cubed minus 2 over s plus 1. And now, from that, we can immediately write down our v of t. We now have 2 e to the minus 2t plus 3 e to the minus 2t with a t in front of it, plus 2 over 2 factorial, which is just 1 t squared e to the minus 2t, minus 2 e to the minus t, again t greater than or equal to 0. And that now allows us to quickly do this partial fraction expansion with repeated roots using the expand function on your calculator.